There we go. All right, let me open this so I can see what's going on in the other window. There we go. All right, so we have the midterm coming up on Tuesday. It is over the topics in both of our homeworks, which also happens to be quiz 1 and 2. So let's get it. So basically, we're just going to make a formula sheet for this, John. Make sure everything's going well. So considering that you said you had a decent score on the past quiz, I take it you don't need to go over what occurred here on the quiz. The quiz solutions themselves are pretty good. On quiz 2, the average was, putrid. It was like a 12, which is unfortunate. But I'm pretty sure the only reason it was so bad was because people didn't identify via this 45 degrees. That was a good conductor right off the bat. So they probably burned a lot of time on question 1. And then in question 2, both A and B polarization questions should be kind of a gimme. Like they should be pretty quick. This is circular. I don't remember if I was right or wrong on that. Even so. So everything kind of a gimme for these things. In general, really, as she mentioned in class many a time, if you understand what the question's asking, you're set, because you don't really need to understand how to apply the formulas or anything because they're just written on a note card for you or a formula sheet for you. So you really just need to understand what goes where in the formulas and when to use formulas, when to use certain relations, so on and so forth. Kind of covers everything. So we don't have anybody asking questions this time because it's just me and you. So I guess we'll just design a formula sheet. So I have 2 formula sheets. Honestly, I'll take a picture of these things, just send them to the group me so you can see what I've got. And so everyone else will also be able to see what I've got.
Yeah.
And then from there, you can argue to add or take away things as you see fit. We shall address that as it comes up. All right, take a picture of this. All right, first formula sheet I'm sending is quiz 1. So the first half of formulas. Next formula I'm sending is quiz 2, which is the second half of formulas / relationships. Quiz 2-1 is a lot more information packed because of all the little relationships.
Yeah.
There we go. All right, so those are the 2 things I've got. So now I can do this clever thing called pull the group me into my shared screen and look at the pictures. So this is the quiz 1 formula sheet, the quiz 2. So she stated that on the formula sheet or whatever, we can just have a double-sided piece of paper as our formula sheet. No worked examples. Don't try and do that. And we just got to put everything that's important. So basically, we have this one and we have this one down here, quiz 2. So really, do you see anything on here that shouldn't be there? Either 1 or 2?
No, everything looks like it. I mean, it has a place, obviously.
Yeah. And then there's also the, is there anything that you may have had that isn't on this or the other one?
I filled up my sheet. It's the problem. My sheets were like filled with like extra information just in case.
Just in case.
Something. Yeah. But really, I mean, like, I guess yours is more of like a condensed version.
Yeah, in my opinion, when it comes to, so this isn't an open book kind of test, so it's not as bad.
Yeah.
But in recent time, we've seen a lot of open book, open notes tests, and I think that those are actually scams. Because what's going to end up happening in a test like that is you're going to feel a little overconfident, so you don't review as good. And then because of that, when it finally comes test time, you're going to start scrambling around trying to find what you need to find, and you're going to be burning time. And that's the biggest thing that will get you. Of course, given the textbook, I'm sure you'd eventually be able to solve all the problems, but you have an hour and 20 minutes, so you don't have that kind of
time.
Take
you a while.
So I subscribe to the minimum amount of required information to minimize the amount of searching time. The one thing I'm missing here is descriptions of what these things are and where they're useful, but that's just because I remember them, at least, when a relationship is useful. But in general, based on the questions she asks on the quizzes, which is you know, in the first quiz, which is a little while back, it was a single question where we were given an electric field intensity and then had to convert to phasor, which is big. I'm sure there's going to be several
Yes.
phasor questions on that exam,
She
whether or
said
not.
well, she said there's going to be at least a phasor and a polarization. She said those are like definitely going to be on there.
So
So just expect them.
as in, it could be either a single question, like on quiz 2, with regards to the
Mhm.
polarization, where it was just given function, tell me the polarization, or it's going to be like this, where it's a composite of a larger question.
Yeah.
Both of those are easy money, in my opinion. I don't think it's too, it shouldn't be too difficult to get those questions.
No.
So, you know, given this one, the solutions here are actually really well written out, but even so, quick phasor shifts here. The first thing to do is, if ever given a sine function, always convert it to cosine, since we've just arbitrarily decided that cosine's better for phasor. Just why not?
Yeah.
And then you just take the real version of that, which you just convert it into exponential form as follows, which all that entails here is you take the cosine, you replace the cosine with an e, and then you raise the argument. Well, in this case, yeah, you raise the argument to the power of e, and then you do some magic math that allows you to pull out the j omega t, and then you add this, of course, the j omega t, negative j omega t.
Yeah.
Which is up to you.
I guess the main thing would be like making sure you know your Euler equations and like how
Oh,
to
yeah.
convert stuff like
Well,
that.
first off, for those who haven't taken 3D2 yet, if yeah, Euler never goes away. So you might as well master it now. You don't get to forget
never
it. So yeah, and then you'll get to like active reactants and a bunch of other poison. You'll be like, oh, what does an inductor do? And then your life's gonna end when you find that out. So unfortunate. But yeah, then there's, you know, the thing is, it very much appears that she likes to, she's mentioned this before in class, that she, of course, we could be like on some homework problems. We've been given problems that are extensive in, you know, terms of computation and such. And because of that, it's very important. Why is there a guy named Booty Eater in Steam? Even so, it's very important that, what is it? It's very important that on the homeworks, at least, things become very computationally intensive. There's a lot more work to be done. But she's mentioned this, and both of her quizzes, I believe, stand true to this. She doesn't like to do that in a time scenario. She doesn't give us homework level intense problems unless there's some of the simpler ones. And the quizzes, as we've seen in both quiz 1 and quiz 2, the amount of work fits on half a page for 2 problems. It's very, very condensed. And the reason we get away with this is I sit near the front of the class, so I'm able to see what people are like vaguely writing on their papers on a quiz submission day. I kind of do this to compare, you know, if there's a lot more work on everyone else's papers, I might have messed up. And I felt like that a little bit on the last quiz day, but it turned out that was the opposite of what occurred. And it's because people didn't catch this. She likes to give us the simple cases with the tricks, but she doesn't outright tell you. She'll give you this, and then you have to, you know, pick up on it. Of course, if you used the general formula, you'd get the same answers here, sure, but it takes forever.
Yeah, take like way longer.
Yeah, and time sinks are the death of college students on an exam. Everything's about saving time. So in this case, you know, she'll give us questions that are relatively simple and quick to solve. You just need to identify, once again, what's being asked and what's given. In this case, I know a lot of people definitely missed out on this telling you it's a good conductor. So, you know, they had like half a page of just the general formula, which is annoying. Even so. And same here, you know, again, you can just say something like this, you know, free space, done. If you didn't remember this, you'd do the math and get the same number, and yet you would still have wasted a lot of time there. And that's no fun. And then, of course, phasor form of, you know, what is that, conduction current there? No, that's displacement current.
Yeah.
Yet again, phasor shift is done the same way for all things functionally. Now, we haven't really done much pointing vector wise on quizzes or anything. I don't know if we'd be given trickier stuff regarding that kind of stuff, but it'd probably be pertinent to look over some of the homework solutions she has.
Yeah.
To really, because the homework averages are slightly better than the quiz averages. I think they hover around 15.5-ish. And, you know, the homeworks, like the mid-range homework problems and quiz style problems are the type of thing we'll see on the exam. Did she mention how many questions in total?
I don't think so.
I don't think so either. Yeah.
Not that I can think of.
Yeah. So it'll be like that. It shouldn't be too tricky though, in my opinion. But
No.
there's that and that. So back to bonk this. So as you can see, I put down, what is that? That's curl of H, right?
Yeah.
Yeah, curl of H. So just have that because it's used fairly often. It was used on quiz 1. It's not a tricky formula. It's not a tricky thing to perform because it is just the what is it called from calculus? Cross product, right?
Yeah.
It's just the cross product, but with different parameters. And, in my opinion, you don't even actually need to write down that whole, absolute value, even though it's not actually absolute value thing. Instead, you can just write down what I wrote, what it's equal to on the left, just the relationship directly. That's a lot
Mhm.
simpler. And that's exactly how you implement it anyways. And then down the line, another again, curl of H is also equal to the conduction current density plus displacement current density, which those are equal to, that stuff. That's obviously going to be there. We saw it on the quiz. That relationship's definitely, and we've seen it on the homework a million times. That example or topic's definitely going to be there. You can see I have my Euler stuff, the cosine shift, or I should say cosine to Euler, which allows you to then, do the phasor form there of converting the j omega t into the and get that out of there. And then you can also see that j omega t in itself is equal to cosine omega t plus j sine omega t, yet another important relationship if you want to convert it back. All the other little tricks and tips and all that stuff down the line. Another thing, you can see at the top of mine, I wrote mu naught and epsilon naught and their exact values as I remember them, because I always struggle a little bit remembering the exact number mid-exam. So it's best to have those written down. Now, of course, if you ask her for a formula or a constant, she'll give it to you. And in most cases, if you noticed in the middle of quizzes, sometimes she'll write out mu naught and epsilon naught, and it's because I say, what's the value for mu naught or epsilon naught? Because I either forgot to write it down or I just want to confirm that I wrote down the right number, and she'll do it. So in that respect, she might give it to you anyways, but it's just good to have it yourself just to yet again save time. You can see down there I have the all the way at the bottom, I have the displacement current and conduction current in phasor form, which is also very important to know because I believe in one of the quizzes we had to write the conduction current, no, displacement current. Let's get this right. Bonk.
It was the displacement current, I'm pretty sure. Should be quiz 1, yeah.
Yes, displacement current.
Yeah.
In phasor form. So as mentioned, phasor is going to be big. Phase shift stuff, yet again, rather simple. Let's go over and grab the course notes quick on phasor, on just the, not phasor, on the rules for polarization, and go over them really quick. They're pretty important. What lecture would I think has this? Or slides, I should say. Probably this one. Is this it? Nah, it's talking about skin depth. You think skin depth will show up? Didn't show up on the homeworks.
If it's, I feel like if it's a good conductor or something like that, and she tells us or like something of the sorts, I think it might be on there. I don't know.
Yeah, I think wave propagation was, we haven't done homeworks on that yet, so I don't know if it'll even pop up. Have we done a homework on wave propagation yet or no? I don't think so.
No, I don't believe so.
Done, yeah, so it probably won't pop up. That's probably later. Is this gonna be it? Finally.
She did go, or she did talk about what was it? Let's see if I can find it. I don't know if it's gonna be on there or not, but she did talk about the what's it called?
I found it. Here it is.
It's the complex so and so. What is it?
Conjugate?
No. Let's see if I can find it. You can go ahead. I'll just try to find this real quick.
Someone messaged me and grouped me about the Zoom link here. There you go.
Complex permittivity. She did talk about that, like in the actual, like in the midterm review class. She did bring that up. So
What topic does that track with again?
that goes with the lost tangent type
Ooh,
stuff.
Wiki wacky. Well, I might need to cover it. Even so, we'll cover polarization here. Let me check quiz 2 again. Yeah, in quiz 2, lost tangents this stuff. So it
Yeah.
can come in. It can come in, yeah. It can pop in.
Yeah, but I mean, like I said, she did bring it up, so it just makes me kind of think that it might be on the
Yeah.
midterm, just because. I mean, I don't know.
Good focus there. Yeah, so we have our 3 types. Our general type, which is elliptical, circular and linear are both simply special cases of elliptical. So there's all these little things, but all of this doesn't really matter for our purposes here. So let's go to the quiz 2 here to get a practical example. So given, this formula or this formula, either of them really, we can know a couple things. It says determine the polarization. So we have 2 things here. We're given cosine and sine. First thing to notice, the magnitudes of these 2 are the same. That immediately eliminates elliptical out of the possibilities here, because the magnitudes of these 2 components are related to the magnitudes of the what are they called in geometry with regards to ellipse? The semi-major and semi-minor axis. Is that it? Let me confirm. Semi-major. I feel like that's for semi-major axis. I feel like this is in response to orbits. Nope, I was right. That is just how ellipses are described. So the semi-major axis would be the longer radial component as part of an ellipse, and then the semi-minor axis is the shorter radial component as part of the ellipse, which allows it to be, wider in one axis and shorter in the other. That's all that is. So what that allows us to know is via the ellipse formula, the 2 components or the 2 magnitudes following 2 components in different directions are going to be, the semi or the major and minor axes, magnitude. Well, it stands to reason that if the magnitudes are identical, then that means the axes are the same length, which means that you can't have an ellipse anymore. It now falls into one of the special cases, circular or linear, because if they're different lengths, then you can immediately stop right where you are. Actually, no, that not quite. You can definitely, if they're of the same lengths, it's not an ellipse. If they're of different lengths, it could be an ellipse, but I think it can still be a line, can't it? Even with different lengths. With two of the different magnitudes, can it still be a line, or does that not count?
I'm not.
I think line has to do with the phase shifting. Even so, we'll get them. So right here, given this example, it's not going to be elliptical because it has the same magnitude. First off, well, the next thing is to check for phase shift. So cosine minus 2 pi, important here, and sine. If there wasn't a minus 2 pi, then this wouldn't be linear because there's a phase shift and we would say it's circular. But there isn't a phase shift here. Why? Because cosine, with the parameter of minus pi over 2 inside of its argument, turns into a sine. So what you actually end up having is a linear polarization of this wave because it's got, 0 phase difference. Let's look at her slides here. EOX, EOY. Yeah, so it's got the same phase shift. And theta is equal to this. Yeah, so I think linear definitely could have different magnitudes. But even so, the giveaway for linear is that it's doesn't have a phase shift. Because then what happens?
And make sure when you're doing the phase difference, make sure you take the phase of the second one minus the phase of the first term.
Yeah, it's got to be second term minus first term phase. But a good trick here is for this one specifically, you can immediately know that when you subtract the pi over 2, you're going to get sine to sine with no other argument shift, which means they're going to have the same phase. So you have a phase shift of 0, so you have linear. Now over here at B, this one ended up as a circular, and we can check here. So first things first, the magnitudes are the same. So that cuts out elliptical. But that also leads us on to the concept that this might be circular. And now we look. Now this is the exponential domain as opposed to the trigonometric domain. So we can check the parameters here. So we have j 10x on both sides, and then we have a pi over 3, negative pi over 3, and then we have positive pi over 6. Well, what does that mean for us? Well, for circular to be a thing, it needs to have the same magnitudes and a phase shift of 90 degrees between its components. Well, we have pi over 3, which is 30 degrees. We have, no, wrong. Pi over 3 is 60 degrees, right? Yeah. And then we have pi over 6, which is 30 degrees. Now, the thing to consider here is, as he mentioned, second term minus first term. What does that do? Well, we have pi over 6, 30 degrees, minus pi over 3, which becomes plus pi over 3, which yields us 30 degrees plus, what is it? 30 degrees plus 60 degrees is equal to 90 degrees. There we go. Circular polarization, because, as mentioned in the solution, two orthogonal components in space with a 90-degree phase shift, which is computed as follows here, and they have the equal magnitude. So those satisfy the two conditions for circular. Elliptical is the easiest to identify, because all you need to know is if the magnitudes are different across the components, and if the phase shift is something wacky besides 0 or 90, it's just going to be the general case, also known as elliptical. In my opinion, polarization questions are rather quick and easy. There's technically zero computation required by hand, unless you really need to do so with regards to the radians. If you want to plug that into a calculator or such, go crazy, I suppose. But nothing too tricky there. And now we gotta discuss these the rules here to decide upon your conductor, because that's definitely going to be something good. So let me go here, because I wrote a lot of these down. So I have my conditions down here in the bottom right. I also have the loss tangent formula down here, which, as she mentioned, or as Garrett mentioned, loss tangent probably might pop up. So just make sure you have this ready, this little formula. Rather simple formula to remember or write down. We don't need to remember anything. So I have a couple things here. I have specific chunks for lossless and free space, but I also just have the conditions for everything anyways. So the conditions for free space: sigma is equal to 0, epsilon is equal to epsilon naught, and mu is equal to mu naught. Free space is the ideal, in my opinion. The conditions for free space simplify a lot of matters, but I doubt we're getting free space. So next one we want to do is lossless. When I wrote lossless die, I'm pretty sure that meant to say dielectric, but I just didn't write it all the way. So I'm gonna go to lossless dielectric, which epsilon's approximately sigma is approximately 0, epsilon's equal to relative, or epsilon r times epsilon naught, and mu is equal to mu r times mu naught. And then sigma must be significantly smaller than omega times epsilon. A lot of people have the question, what does significantly smaller, significantly larger actually mean in reality? In general, rule of thumb is it's got to be 3 orders of magnitude larger. That's just how it is. That's how I've been told, at least. Those are the conditions to identify that situation. And then you'll have lossy dielectric as opposed to lossless, which is sigma is, I think I meant to say not equal to 0 there, but I just didn't write the 0. So let's go. I didn't write lossy anywhere else, so we'll just assume that's the case, unless you know that for sure. In lossy, I'm pretty sure sigma has to not be equal to 0. Right?
Well, not quick. And lossy?
Yeah. It's not equal to 0.
You said sigma?
Yeah. What's sigma meant to be in a lossy dielectric?
I'm not 100% sure. I don't even think I wrote that down.
Yeah, I think it's not equal to 0, because I don't see what else it could be. But next on that, after that, is its epsilon's going to be equal to epsilon r times epsilon naught, and its mu is going to be equal to mu r times mu naught. Really, most of the time, you can identify what it is based on its sigma, except in the case of lossy. Well, actually, even so, you can still just calculate omega times epsilon. Even so, next we go down to the good conductor, everybody's favorite. Sigma is equal to approximately equal to infinity, or also known as just a big number. epsilon is equal to epsilon naught, mu is equal to mu r times mu naught, and then sigma is significantly larger than omega times epsilon, which means at least 3 orders of magnitude larger. Relatively simple calculations. Now there are some other quick tricks you can see right here. One of the rules for good conductor, I have all the good conductor relations right up here, which is alpha will be equal to beta, which is equal to square root of omega times mu times sigma all over 2. Simple one here. And then we have, I don't remember what the name of this is. It's lowercase. That's delta, isn't it?
Yeah, it's delta. Yeah.
Delta is then equal to 1 over alpha, 1 over beta. So, you know, even Steven. What is this, lambda or gamma?
Gamma.
Gamma is equal to, you know, I don't even know if you've ever been asked to calculate gamma, but it's actually a very quick one. You just tack a J onto B. Simple. And then funny N, also known as what in Greek letter to speak? Eta? No. Let me check if it's eta.
Yeah, it is eta. I remember. I believe.
Yeah, I think it's eta. I'm gonna check it out.
Right.
Eta Greek alphabet. I'm sure. Yeah, it's eta, all right.
Yeah.
Capital Eta. Capital A is just a big H. It's just a Times New Roman H, but the lowercase is that for some reason. Even so, the relationship that was able to, you know, speed run you through the test if you were paying attention is this whole thing right here, which is just eta is going to be equal to square root of omega naught times mu naught over sigma at the angle of 45 degrees. This parameter doesn't, no one cares about this parameter. All you need to care about is that it's eta at 45 degrees. Immediately know it's a good conductor. And you can follow through with all these other relationships, which are very, very helpful. But as mentioned, this little brick down here is the conditions. Honestly, my handwriting is not that good, and I kind of smushed it all together. If you're smart, you'd probably want to draw out like a little bit of a table on your notes card just for the conditions, because they're actually pretty big. And you can see I have, you know, specialized formulas for lossless, free space, so on and so forth. Good conductor. I left out lossy because lossy is probably, in my opinion, the most unlikely condition for us to get. We're either going to get free space or good conductor or lossless. I don't think we've ever even seen a lossy example question once. In either homeworks, maybe in class, but in homeworks or quizzes, I don't remember anything lossy. I just remember lossless, free space, and because lossy is the most complex one to compute, which is, as mentioned previous, she tends to avoid overly complex computation, instead opting to give us, you know, like good ones that if you know your stuff, you'll find the quick tricks and be able to speed run it. But even so, we have other stuff like wave velocity is omega over beta, and then we have wavelength, which is simply 2 over omega then, or 2 over beta, so on and so forth. How's it going, Eric?
Hello.
What's up? Yeah, we're just going over formula sheets and some other stuff. We just touched on polarization, and we'll probably jump over to some lost tangent stuff since it was mentioned. I posted both the formula sheets that are both of my formula sheets I use for both quizzes in the group me. That's what we're using to view them. But we're allowed 1 double-sided formula sheet, no worked examples on the midterm. So I recommend going through my formula sheets and your old formula sheets and writing down what is important. On this formula sheet, you can see in the middle of my thing, first off, I have the general formula for alpha, and then I denote that the only difference between the general formula for alpha and beta is that this one is positive in beta.
Yeah,
to save me the time of,
right there.
Yeah, to save me the time, or to save me the room and time of writing the whole thing out again. And then you can see another thing right here, that if alpha is not equal to beta, then it is lossy. And that's the whole reason why the computation is so intensive for lossy, because you have to do the general formula for both alpha and beta, which is annoying and slow. So that's just an important thing. But you can see I have the power average function thing. We've never used it on an example or anything, but it's in the notes and it's in the book. So I wrote it just in case, and it didn't show up. And I don't really know how I would use it, but since it wasn't really an example or practice problem we've done, I wouldn't expect it to pop up. But it's, you know, we'll have more than enough space given two sides of the sheet of paper. So feel free to put any formulas you feel you might want, even if it's just for security's sake.
I'm probably gonna type mine up because
yeah, that's allowed too.
Yeah, make it a little bit nicer.
Definitely
easier to read.
Pointing. Oof. I remember, yeah, this is the power thing. That's where the pointing comes
Yeah.
from. So this is what that is, and this is something that I feel like might show up. Simply since it's a part of the thing, I just don't remember us doing any examples with it. The other thing is what? That's complex conjugate of
Yeah.
yeah, the complex conjugate
Yeah.
of the phasor form of H.
Yep.
So that's a whole other thing. Complex conjugate. Anyone remember the rules for complex conjugate?
You take the I and change the sign.
Yeah. Another thing I've found is to actually compute it given a calculator. Complex conjugate is normally just the well, yeah, that's basically it. I'm thinking
Yeah.
of a different trick.
On your equation sheet, did you have like the, I guess that sort of,
Which sheet you talking? Which quiz topic?
it was like our first quiz.
All right, I'm looking at it. You should be
Okay,
able to see it too.
yeah. You don't have the equation for like, um, what is it like for with regards to force and the sliding bar and a magnetic field sort
Yeah,
of.
I didn't pop those in there. Those wouldn't
Okay.
definitely wouldn't be a problem to have those since they were actually pretty big homework topic.
Yeah,
Yeah.
I don't remember them off the top of my head, but
yeah.
they're not that complex.
I don't feel like having to rederive them, so
Yeah, well, have them if you want them. We'll have more than enough space, which is perfectly okay. So that's that. So going back to some, I don't even need to keep doing that. I could just do that instead. So this is some pointing vector stuff. Lost tangent would probably be in this one. Unless I'm mistaken. No, it'd still be in the last one somewhere. Or actually it might be here instead. Let's see. Yeah, it's right here. So this slide right here, that being September 16th, chapter 10, lecture 9 slides, start off with conditions and just have whole slides of conditions and relationships you can use, which are awesome. This right here, you see, here's something I don't like. So my handwriting's hot trash, right? So we have mu, which in most cases, particularly here, is written as mu naught times mu relative, which means that you're writing mu. But my mu looks an awful lot like my u. So when I write this formula, as seen in my formula sheet for quiz 2, I write it with a V just for wave velocity, even though I know in electromagnetism and electronics and stuff, V is normally, say for voltages or something. But even then, I don't care. It's V to me. It's velocity. I've taken enough physics classes. So this equation right here looks a little wacky, but it's just wave velocity equation, omega over beta, which can be rewritten as such. Even worse, you could write the relationship where mu and u are in the same formula. So I don't like it. It's poo-poo garbage. Not a fan. But that's just convention. Use convention as you see fit. So then this is intrinsic impedance. Right here. Eta naught, is that intrinsic impedance?
yeah.
Yeah, okay.
Yeah.
So this just looks like it's that number. So you could just memorize that. That's a
Yeah.
constant.
I thought you were just
down.
stating it. I didn't know you were asking this.
I just wanted to confirm it because I've been calling it eta, but I feel better if I just call it what it is, which is, intrinsic impedance in this case. And then this is just impedance given whatever your case may be. Now, this is the lossless dielectrics, which means here's all your cases. I wrote most of these in the formula sheet. Down here, everyone's favorite relationship. Don't get your directions wrong. If you get your directions wrong, you deserve a 0. We have free space conditions, good conductor conditions.
Yeah, and don't forget when she says like when if
Morskin
we
effect
get a
stuff.
question saying like non-magnetic, geez, can't talk. If it says like non-magnetic, make sure you do, or make sure you know that's mu naught
Yeah.
for that one.
When you say non-magnetic, that means it's mu is equal to mu naught, which classifies it as
Yes,
a
exactly.
lossless. No, not lossless. It classifies it as a free space, I think. Yeah. What'd you say?
Uh,
What'd you say, Eric? You're a little quiet.
I was asking you to repeat what you said.
Oh, so the test is about picking up on all the little, quick tricks that allow you to simplify problems. One of those quick tricks is identifying, what material you're doing your propagation through, right? Well, one of those cases, on the quiz, we got good conductor, which is a simple one to identify. But then there's free space, which normally you'd think is rather simple, but it's unlikely that it'll just outright say free space. Maybe it'll say, your wave is propagating through a non-magnetic material. What
Well,
does that
not
mean?
necessarily.
Yeah.
Not necessarily.
Yeah.
What else?
Because on
Because
quiz
non-magnetic.
2, it says non-magnetic medium, but it's still a good conductor.
Yeah.
Oh yeah, because let's see, where's good conductor? It should be down here. Oh, well then in that case, if you're given something else, because then
Just make
it's-
sure you know it's mu not.
well, it's
Like if
it,
you're given
and
non-magnetic, just make sure you know it's mu not.
well in this one, but if good conductors are if that one, then this would also be mu not. I guess the relative, I don't know. Who knows? Even so, so all you're saying there is just use that as a point to identify what your mu is.
Yeah.
Yeah, yeah.
Alright.
I guess you just know non-magnetic means mu not, but it doesn't imply anything else.
Yeah. All right, good. That's better. No, those are all the relations. So these are all the relations that you'll need to know. Except I don't see lossy here. I see lossless. Let me go up again. I see lossless. I see good conductor, free space, more good conductor stuff, skin effect and skin depth and such, which might be good to have,
Yeah.
depending, really. But that's all there is on this one. And yet again, our favorite, much less or much larger than, which, rule of
Mhm.
thumb, 3 orders of magnitude smaller or larger to
So-
satisfy this.
It's 1,000 or so.
Yeah, basically. So yeah, so this is a whole thing. This actually becomes very important when you start messing around with circuits in general. When you start pumping high frequencies through stuff, turns all my wires into resistors. But even so, we haven't had to do. Have we done at least a homework problem on this? I don't recall. I mean, probably from homework 2 if it's anywhere.
I don't know. I know we definitely did an example in class, but
Well, yeah, I would assume we've done an example in class, but I believe she stated that with regards to test content, the only topics we'll cover is up to whatever's been covered in homeworks or quizzes, which means up through wave propagation.
okay.
But we're not going to be talking about, reflection incidents and all that stuff,
Right.
which good. I haven't had a chance to touch on all that as much as I'd like.
While I don't remember AC resistance being in or skin effect being in a homework, it's also not terribly difficult. It's just that.
Well, this is it. This whole slide is everything. Now, as
Yeah,
mentioned,
literally.
this only takes effect at high frequencies. What does a high frequency mean? Who really knows? Doesn't really give you a range. Technically, any frequency should cause this. It's just you got to get past a certain point before it's deemed significant, I suppose.
Yeah. Because
Yeah.
well, I mean, it depends on, of course, your wire cross section, right?
Oh, that too.
'Cause
But
if
in
your skin
general,
effect is
regardless of
bigger
the
than-
wire, if you pump high frequency through it, the higher the frequency, the less it'll be touching the center of the wire. You'll just be losing out on all that center. So it should increase its resistance, lose more power. Skin effect's pretty important in, as it mentions, the pure power lines. Yeah. Big sad. But that's just how that works. Nothing too saucy there. This whole slide covers the entire topic matter, which is perfect for
Yep.
us. So that's good. Let me get up. There we go. All right, so that's that. I still wanted to find lost tangent. So there we go. So it wasn't in the 16th, so it's probably in the 7th. Oh yeah, it's definitely gonna be here. Okay,
Yeah.
here it is. Not equal to 0. And she
Oh,
like
okay.
highlighted this for some reason. Don't know why. Probably
Oh,
mentioned
I
it.
don't know.
What did you say, Eric?
It's the general case.
Well, yeah, the general poo-poo case.
So,
The case that we're almost never given on a quiz or anything because she stated she doesn't want us to actually have to go through all the computation when we could instead just identify a quick trick. Well, all this other wacky stuff. I want to get to lost tangent.
the first, like the equation, I guess, earlier in the slides, that differential equation.
Which one? Yes.
That one. Yeah. Have we used that really?
Nope.
Mm-mm. Nope. We
This
haven't.
is just a wacky way to say B is equal to that, I guess. No, it just tells you B is equal to that. I don't know if this is format. It'd be like that sometimes. I don't believe we've used this even once,
Okay.
unless I'm mistaken.
No, I mean I remember we derived it in class or something and then never used it.
Well, yeah, so that'll be why. See, see, like it even says for simplicity, this is it. This is what you assume. This is probably what it is in real. This is what it's like in real life for all those, big boy physicists and engineers. But that's not us quite yet, is it? So go on down. I want to get to the lost tangent because that was supposedly going to pop up. Yeah, see all this funky monkey stuff? That's not gonna doubt it. That's not popping up. This will though.
Yeah, stuff highlighted.
And this relationship's a good one, and this can be written out as many ways as you want. You can calculate the magnitude of H given the magnitude of E or eta, and so on and so forth.
Yeah.
We already touched on polarization, so I just want to. This is the general garbage content that we're all here for. This suffer. And this is it written in Neppers per meter, which is this funky. I love when we tap that 20 log 10 of something. That's always great.
Mm-hmm.
Yeah, see, in lossy, this has to be less than or equal to 45. Although if it's equal to 45, you might be able to assume it's a good conductor. And I say might, which is definitely can assume it's a good conductor.
Yeah.
Here's this right here is our loss tangent relationship. Tan. So when one says loss tangent, the angle itself is, what's the proper name for it? It is,
The angle of
Just a loss angle.
yeah, isn't it literally just like loss tangent angle or loss angle?
It's a loss angle.
Okay, yeah. So when she mentioned that loss tangent might pop up on the midterm, or it's something you might know, it's fair game. It's been on the quiz we were given it, so we didn't have to do anything funky. But when she says like loss tangent stuff, it means you use this equation. It was on my quiz 2 formula sheet just in case. This little relationship pops up everywhere, sigma over omega epsilon. So just I guess remember that or write it down. But then it's tangent of 2 times the loss angle. And then my guess is this time we'll be given something that's not a good conductor or it is a good conductor. And it'll ask what type of material it is at the end or something. And then you'll figure out it's a good conductor by calculating the loss tangent, and it'll be equal to 45 degrees or something like that.
yeah.
But if not, if it's given to us, then easy peasy. That helps us out, doesn't it?
Yep.
And then we just have, lossy, our favorite, this famous loop. Here's a good discussion on the loss tangent.
Yeah.
This is some stuff which allow you to say good dielectric or good conductor. This is another one to classify a good conductor, which also means a very large tan of theta. Just complex permittivity. This is what you're referring to earlier. You
Yeah.
heard something.
Yeah. That's what I was referring to.
So this is.
She did talk about it in class. So
I don't
just have it on
believe
there just in case.
she talked about it, but I don't remember any examples being done utilizing complex permittivity.
Yeah.
Yeah, but like she could just be like on a question, you'd be like, tell me what complex permittivity is, Like you never know. I mean, it's a very simple equation. So
I think it looks like right here that loss tangent is some wacky stuff here. Or theta is just
Yeah,
equal to, it's just a
yeah,
whole
so
thing.
the loss angle. So theta is just the loss angle, and then
Well, theta eta is loss angle, right?
no, just
Or
theta.
okay.
Theta. So the loss angle is equal to 2 times the angle of
Theta
eta.
eta.
Yeah.
Okay, let's get that clear there. So I was wrong then. If you're given theta eta, my favorite new phrase, you will be able to identify if it's a good conductor, so on and so forth. Great. But if they ask for the loss angle and you write theta eta, you're an idiot and you'll lose points when you're actually supposed to double it. Very simple little quick relationship, probably worth like 2-3 points, but 2-3 points is better than 0 points in my opinion. So take it where you can get it. So that's everything on that. So
So you're saying though the loss angle specifically refers to theta eta, right?
loss angle refers to theta.
Oh.
Theta eta will be given or calculated. And then when asked for the loss angle is equal to 2 times theta eta. Theta eta being some parameter that's given or calculated.
Yeah.
2 times theta eta is equal to the loss angle, which is why tan of theta is equal to sigma omega over omega epsilon, which is the loss tangent as defined here of theta, but theta is actually equal to 2 times theta eta. But this is the loss angle, not this.
Mm,
This, like 2 times theta eta is the loss angle, but
that's equal to.
yeah, but theta eta is not the loss angle on its own. It's half of it. So don't boom that. Don't mess that up. So that's that. So let's look. Anything missed here? We discussed polarization. All these funky monkey things are just figure out how to use a formula. Conductivity is, calculate sigma using any number of the formulas already given. Determine direction of propagation. Let's just look at this real quick and define that. That's rather simple. All right, we're given this and it's in the AX direction. All right, how do we define the direction of propagation? All right, look here at this part of the parameter, what's multiplied by beta. All right, we see that it is positive y, that means it's negative y.
Mm-hmm.
Because this parameter is assumed negative, so if it's positive, that means it's in the negative direction. That's all you gotta know there.
Yeah, and remember, beta and alpha are always positive.
Yes, they must be.
Do you remember that?
Beta and alpha are positive for, what's the reason, gentlemen? Because they're defined by the square root. Unless you're trying to make some complex attenuation constants and such,
Yeah.
which is not a good idea because I don't think it exists. You're going to want those all to be positive. And this one gives you the operating frequency. So here's the trick here. Look at this. It says the operating frequency is 5 megahertz. What could she have done on this question? She could have asked us for the skin effect resistance. Because the frequencies have 5 megahertz. That is actually kind of high in reality. So if you're looking at your question and it's, quiz 2 topic type of question, if given the frequency, she can 100% ask you about skin effect stuff. So keep that in mind. So have that little page of formulas written down. Direction of propagation is rather simple. As mentioned, you just take the negative of whatever is currently sitting in the y, or then I should say is the beta parameter. Whatever is multiplied there, you take the negative of it or the inverse. So if it's positive, it's negative, it's positive, real easy. Then you say, how would you classify the material? Here it was rather quick. If you paid attention to eta, eta was at the angle of 45 degrees. That simple trick means it's a good conductor. That's it. That's her justification she wrote here. Theta eta is equal to 45 degrees, good conductor. That's all that's necessary there. Classification materials follows the chart that's on my formula sheet and the chart that was in the slides I showed previously. Or I should say in the slides that I showed previously. I recommend on your formula sheets, you all have a small little well written out chart as opposed to my trash handwriting where you can very quickly identify what's what. Classification materials, also easy points. Conductivity of material is use any formula you'd like. In this case, since we were given, eta, we were just able to simply compute. Nothing too difficult there. It's just 100. 100S, what is that? Sieverts? What is it? No. Siemens? Okay.
Yeah, Siemens.
Siemens. Siemens or whatever.
Yeah.
Oh, it's right. Sieverts is not it. That's something else.
Radiation.
Yeah. My favorite type of measurement. I love measuring all the gamma rays I consume on a daily basis.
Yeah.
Then on D, we determine alpha, beta, gamma, and the electric field. So real quick, this one's real fast when you're talking good conductors because alpha and beta are approximately the same, and they're also approximately equal to a very simplified formula of the general case. So you can just multiply through and get the number. Gamma is nothing more than tacking a J onto the B and summing the Jones together, as you can see. The magnitude, as mentioned previous and on my formula sheet, of E, if given the magnitude of H for which we were, that would be 10 here, is the magnitude of H tacked onto the front. Wait. Yeah. Yes, it is. There's this extra bit, but we don't have to consider that. That's a whole other thing. So this is H naught, in this case 10. And then down here, as you can see, if you multiply that by the absolute value of theta eta, if you multiply that by the absolute value of just eta, you'll be able to find yourself E naught, which in this case is just 2 pi, easy peasy. You can find yourself the direction right off the bat using the funny little circles, or in this case, cross product rules. It's negative Z direction. Down here, we got to do some little funky shifts. So first things first, we calculated all this stuff, which doesn't change. between E and H, they're still the same. In this case, we were just given this without anything plugged in because we were going to be asked to calculate it later. But since we already have it now, when you write out E, you should plug it in. So when you plug a negative 2 pi E to the, this is alpha times Y times cosine 16 pi. In this case, 16 pi is equal to omega. Where did we get omega from? Bonk, 5 megahertz. Omega is equal to 2 pi F, right?
Mm-hmm.
Yeah, so in that case, you can see
Correct.
that all they did was, do some funky math and produce 16 pi times 10 to the 7th power, which should be 2 pi times 5 megahertz, something like that. Not quite, some off there. Actually, no, there shouldn't be something off. That's exactly what it should be.
Yeah.
So I don't know. That's 2 pi F means 5 megahertz times, in this case, 5 megahertz times 2 pi. That's going to make, your stuff. I don't know where the 16 pi, I think that meant to be 10, right?
Probably.
Yeah, even so, that was supposed to be a 10. Who cares? Times 10 to the 7th power, so on and so forth. T, that's intrinsic. This is beta, cool. But you can see, good conductor. What does that mean in a good conductor? I think I lost my half point on this quiz right here, now that I think about it, because I put pi over 2. That is wrong. It does not lead it by 90 degrees. It leads it by, in this case, 45 degrees, right? The electric field should lead the magnetic field by 45 degrees in a good conductor.
Yes.
Does that,
Yeah.
what are the rules for changing that across materials, or is that just the case most of the time?
Your however much it leads, I believe, isn't that to do with your theta eta?
Okay, gotcha.
So
So
that's
does that
how
mean,
much it
does that
leads.
mean it just is theta eta then?
Yeah, basically.
'Cause
So
we-
like you have
Because we
your-
have 45 degrees here as well, as given in the good conductor.
Yeah, so that use that theta eta in terms of how
radians.
much E leads.
Yeah, and that's the trick. So it's in terms of how much it leads. So in an electric field, the electric field leads the magnetic field. So in this case, that means you add theta eta, or in this case, pi over 4, to the electric field parameter of the
Mhm.
cosine. But if we were given an electric field instead of H, like if this were E is equal to this, you do all your math. That means you subtract within the parameter of the H if this were an H instead of an E, because it follows the electric field. So you just got to remember who's first. And E is first because it's the best letter in the alphabet.
Yeah.
Me and Eric know that. Even so.
Yep.
Agreed. Yeah. So we already touched on polarization. So I think we've got most of the formulas down that we could need. I posted both of my formula sheets from both quizzes in the group me for those who wish to view them and use them for what they see, use them for whatever they want. I don't really think there's anything else to touch on, really. I think we got it.
I think we got all. I guess the main takeaway here is make sure you can identify what you're looking for and what you are given.
Yeah, it's always going to be, I doubt we're ever, so we're given an hour and 20 minutes here. There's a lot to cover. I doubt we're going to be given the hardest cases, also known as in any situation, the hardest case is always the general case, because you have to go through all the stupid formula computations for anything, really. General's always horrible. Special cases are always great. It's just kind of how the world works. So as of now, we've been given special cases on quizzes a lot, quick stuff, which is awesome. And hopefully that continues. Brush up on phasers. We haven't had to do it in a hot second since all the quiz 2 stuff and all the stuff we've been working hasn't really been touching on phasers all that much. Make sure you go back and review your homework for your phasers, because phasers are going to pop up again and they're going to come back with a vengeance, I'm sure. So make sure you know your phasers. Pick up on all your little quick tricks, have your tables and everything in your formula sheets. That'll help you a lot. Let's try and make sure the average for the midterm isn't like a 12 out of 20 or something. That'd be no fun. I don't know. Oh well, it's bad, unfortunate. Hopefully the midterm could be the saving grace. I don't see too many theoretical issues here. But sometimes stuff pops up, and if you do get general formulas and general case things, just don't mess up with the calculator. Some of the formulas are a little wacky, and it's really easy to misinput something on the calculator. So make sure you're double checking your stuff. Definitely when it comes to like nested stuff. Use parentheses to your advantage on your calculators. All I should say with that. Parentheses save the day on calculators.
Yeah, one of the mistakes I actually
So
made
do.
on the one of the quizzes was like I didn't calculate one. It was, I don't remember, something over the. It was the velocity equation, and then I
Yeah.
didn't put the epsilon and mu inside the square root.
Yeah, and then you got smacked. Yeah. So yeah, something I missed there. Everybody for your quiz for your formula sheets, because this is probably going to pop up since it showed up in the homework, and it's pretty standard electromagnetism question. Go back to your homeworks and get down the formulas we used to calculate the force/velocity felt by a bar in an electromagnetic system. Just, like, get it moving in a direction. That formula is definitely some top tier loot, and it's worth having on your formula sheet. Because I think in every class I've ever taken on electromagnetism, that question comes up.
Yeah.
Because I guess it's a simple way to illustrate that with the right hand rules and such. Who knows?
Yeah.
I've never done it physically because it's I don't like sparks all that much, and my metal would always fuse to the bars. Probably because you're not supposed to use AC current, but oh well. It'd be like that. But that's that. So I think that's probably everything.
Yeah.
I don't remember
I think we
anything
covered
else.
it all.
Yeah. So that's kind of the whole shebang. It's really just the real meta for this class is setting your formula sheet up properly.
Yeah.
Yeah.
That's kind of all it takes, because the lectures are good enough that, she touches on everything. So as long as you show up to lecture, you'll have a pretty good understanding since she's a very good teacher. And then past that, when it comes quiz time, you don't need to memorize formulas. You just need to understand how to read problems that she's mentioned before. She gives us our formulas, as I'm sure most people would have been given formulas. People who've memorized formulas, come on, man. Why?
We call them chemical engineers.
Yeah, unfortunate. Yeah. Please, chemical engineer, tell me what a redox reaction is. Please. What does bleach and ammonia do, chemical engineer? And why did they use it to get rid of ants? All right. Oh, that's now. I'll stop recording. Pop, 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 pop.